Alright, tutorial for video. We have an electromechanical system, we have a resistor, negligible inductance, back EMF here, an invisible JA that we'll talk about in a second, theta M applied here, TM, and we've got M1 here, which is 1, and N2 is 200. These are gears, there's spring, the JL, and that's spring 2, and that's our damper. We want to analyze at each inertia. A JA, which is here, we're going to translate it over here, so we're going to encompass that right here, which is JA dash, TM dash, and theta M dash. Well, here, so the sum of all torques is the TM, and minus TA, and then minus the spring. So like that's the applied, and then this is the internal. We have put the TM dash equivalency here, same with the JA dash, so when angular displacement, the inertia is S squared, the K is no S, and then when we talk about the damper, it'll be just S to the power 1. Instead of destination on source, like these two, we have source on destination. It's probably worth mentioning that the K1 has theta M subtracted by theta L, which is happening over here. So that's this side of it. So it's theta M minus theta L. So that's why we get this equation here. Now, analyzing the second inertia point, JL, we have a spring, the inertia, spring 2, and the damper, theta M and theta L. So theta L is the permanent one here. When we do the K1, theta L minus theta M, we have no applied torque this time, so it's just the inertia, which is S squared, times the theta, D, which is times an S as well, as mentioned earlier. The spring times no S, but theta and the appropriate thetas. There's no translation here, so we don't have to worry about that. Make theta L subject to the equation, so gives you that. That will be our equation. So with equation 2 and equation 1 that we've derived from both inertias, subbing 2 into 1, we'll just sub theta L from 2 right into that. Do this here, we factored out the theta M's. Point is we have this form here. Now we're going to briefly look at the electrical components. So we're back EMF, negligible inductance, so we'll ignore that current, and yeah, Kirchhoff's voltage law, the VEA, the voltage there, minus that, gives you that full circle. We also know that TM equals KTIA and WM equals S theta M. You can just sub that straight in. The back EMF can be that from here, IA, so that we arrange for IA just divide both sides by KT, gives you that, and this from that. Fantastic, so now we have an equation 4. So you sub in 3, 2, 4. TM's right here, so literally just going to slap that bad boy right on there. That big bracket is literally just that TM. It's done some simplifying. Factored out theta M, divide both sides by it, to get you that. We'll just let this be our equation 5. I'm going to sub equation 2 into equation 5. Oh well, yeah, from here, so like just make theta M the subject of the equation. And we sub that right in where theta M is, so I'll just chuck that right here. That's the negative 1, so when we bring it to this side, we can just, so like that's like on the top, and now we'll just put it over here on the bottom. Now it's just a buttload of simplifications. My strategy was to make the denominators for both numerator and denominator the same. Denominator for this denominator in the brackets, and this denominator in the brackets. With that, you get all these, cancel out these two, flipped it to get the right theta L on EA. That's just that flipped, just expanding all these terms out to get that denominator there. Done some simplification, divided everything at the end by JA, JL, R. And then you arrive with this. So this was the final form. Plugged that in all MATLAB and it solved, gave me that.